Okay, good evening. So, welcome to this live session on 12/12/2025. So, from the previous live, okay, so in the previous live session, so what we saw was, so we have seen what is controllability, what is observability, and we also have seen pole placement technique, pole placement method, and we have seen some of the problems and solutions. Okay, so now today's live session. Okay, so what we will do is uh, so we majorly solve one problem related to controllability and observability. Okay, then we will see the important part, which is the state observers. So majorly we will see the content revisit to understand important part of the state observer, and then we'll see the we'll understand the concept of Kalman filtering, and we'll do one example for this. Okay, so let's start it. So starting with the one problem on the controllability and observability. Okay, so let's say uh, so we need to show so that the pair AB is controllable. So if and only if A transpose C transpose is observable. Okay, so let me expand this page maybe. Yeah, so that you will see the entire page. Okay, so for a given linear system, okay, so we need to show that the pair AB is controllable if and only if so A transpose C transpose is observable. So and vice versa also. Okay, so it means that A transpose and C transpose is controllable and AB will be observable. That's what we need to show. So we already know the, let's get the equations first, which we know. So x dot is equal to Ax of t plus B u of t, y of equal to Cx of t plus D u of t, where we know all these definitions. Okay, so controllability matrix. Okay, so controllability matrix we have. Okay, so represented with capital C. Okay, so controllability matrix can be written as B, A, B, A square B, etc. A power n minus 1 B. Okay, so system is controllable if rank of C is equal to n. Okay, so where n is nothing but the order of the matrix, uh, size of the matrix A. Okay, so if it is full rank, you can say that every system can be influenced by the input. If rank is less than n, we can say that some states are not controllable. Okay, so similarly, this is the controllability. Similarly, we can define the observability. So matrix O is can be written as O is equivalent to C, CA, CA square, etc. C A power n minus 1. Okay, so again, system is observable. Okay, if and only if. Okay, so rank of O matrix is n. Okay, so these are the two things we have. Now get back to the question. We need to say, we need to prove that. So the AB is controllable if and only if this is observable and vice versa. Okay, so let's start with the basic one. I hope what we can do is we can start with the AB is controllable and prove that A transpose C transpose is observable, or else we can start the other way around. So we can start with A transpose C transpose is observable and prove that AB is controllable. Okay, so we'll do both the cases. Let's start with the first one. Okay, so so let's start with the first one. Okay, so let's start with the controllability matrix. Okay, so the controllability matrix says that so B A B A square B, so etc. A power n minus 1 B. Okay, so we can say that so the C is controllable. Okay, so if the rank of the C matrix is full rank. Okay, so similarly we can write the observability matrix. Okay, so observability matrix as a C transpose C transpose A transpose C transpose A transpose square etc. C transpose A transpose whole power n minus 1. Yes. Okay, so now let's take the transpose here. Let's say if we consider this. Okay, let me remove this. Okay, so if we take the transpose, what we will be getting is we will be getting the same entire matrix. Okay, same matrix. So same matrix. So let's say we are transposing it. Okay, so how do we write that? We could write like C transpose whole transpose. Okay, then so we could write it like we are taking the transpose. Okay, so A transpose C transpose whole transpose. Okay, so A transpose square C transpose and then whole transpose etc. A transpose n minus 1 C transpose again whole transpose. I think this step is straightforward. Okay, so which will we have used this identity. So AB transpose is equivalent to the B transpose A transpose. Okay, so now in this equation, so let's say if we define so the matrix C is equivalent to B. Matrix C is equivalent to B. So what we can get? So we can get this one as B because C transpose whole transpose is C, so that will be replaced with B. And here we get AB because this will be like C transpose A transpose. So we get AB. Okay, then here we get so A square B etc. A power n minus 1 B. Okay, so now what exactly is this? This is nothing but what? This is the controllability matrix of, so this is the controllability matrix of AB. Controllability matrix of AB. So here we know that here O is full rank. O is full rank. So then, so the C of the pair AB controllability matrix is also a full rank. Is also full rank. So So we have started at observability matrix of C transpose A transpose. Okay, so this is like this is observability matrix of C transpose, observability matrix of A transpose C transpose. Okay, then we were ended up with the controllability matrix of A comma B. Okay, hence proved. So we have started here and we ended up here. So that's what the question is. So if A transpose is observable, we have to prove that AB is controllable. So we have started with the observability matrix of this with rank full, and we have shown that controllability matrix AB. Okay, so this is the proof. Okay, so now we will look at the other way around.
Uh,
So
Sir, what is the C
yeah,
double dot equals to B? That let's
which
define
one?
at last you. At last you
Yeah,
written.
here. So we are defining C here is equivalent to B.
So what C double dot that
No,
is
no,
to
no.
you?
This is definition. Definition.
Oh, okay. Okay. The
It's a
C equals to
mathematical
B. Yeah,
symbol.
just
No, no, no. This symbol means defining.
okay.
It's mathematical symbol.
So we are just writing C equals to B.
Yes, yes,
A case
exactly.
we are okay. Then
Yes.
only
So
our
because
condition.
of that, yeah. Okay.
Okay.
So the we'll start the other way around. It means that now we'll start with the controllability matrix. Okay, so controllability matrix is equivalent to B, A, B, A square B, etc. A power n minus 1 B. Okay, so similarly, if you take up the transpose for this, so you'll get what? So B transpose A, sorry, you will get B transpose A transpose B transpose A transpose square, etc. So B transpose A transpose whole power n minus 1 whole transpose. So you have to check this. Okay. So the individual matrices gets transposed and whole matrix also gets transposed. Okay. So just like the previous case here. Okay. So here if you define the matrix as C transpose equal to B here. Okay. So this means that B transpose equal to C. Okay. So that's it. And we also can define A is equal to A transpose that we have already. Okay. So then, so C transpose can be written as C A. Okay. So C A square etc. C A power n minus 1. So whole transpose. This is nothing but what? This is nothing but C A square etc. CAN minus 1. Okay. So which is nothing but observability matrix of A comma C. Okay. So here in this case we have started with so controllability matrix of we have started controllability matrix of okay controllability matrix of A B. Okay, so we will end up here with observability. We have started with the controllability matrix of A transpose B transpose. Sorry, this one. So controllability matrix of A transpose B transpose, and we end up here as observability matrix of A comma C. So here this one has full rank n. Okay, this would also have full rank n. So that's proves the other way around. Okay, so this is one important aspect which we call this is as the duality property. Duality property. Okay, so this is one important problem I wanted to bring to you. So related to the controllability and observability. Okay. Next, so majorly these are the two equations. These are the two, controllability and observability. Okay, so concepts which are very important in the state space analysis. Okay, yeah. Next, we will get to the observer design. Okay, so in the observer, basically, we have seen in the previous uh, class, okay, previous live session, that that we have seen this pole placement approach. Okay, so basically pole placement approach is a design problem where you wanted to place your closed loop poles to your desired locations. So where we have seen three methods in the pole placement. So direct method. Next is using the similarity transformation method. Okay, so using the transformation. Third one is the Ackermann's formula method. Okay, so which all these methods will help us to put the poles in the desired locations. So if you remember properly, we have this equation for pole placement design. Control law looks like U is equal to minus kx. Okay, where k is the gain matrix, x is the state. Okay, it means that to find the control input u, we must know the main thing is we must know, okay, the x. Okay, it means that all these states must be available. Whereas in the practical practical cases, sometimes all these states may not be available to you. Okay, some states may be available. Let's say, for example, x is equal to x1, x2 if you have. Okay, so if your y equation is like this, if your y equation is so 1 0 x1 x2, it means that your y equation is only x1. Okay, your c matrix is this, your x matrix is this. So now what is happening, because of c is 1 0, y is x1 only. It means that, so if you know y, you can able to find only x1. You cannot say anything about the x2. It means that x2 is not available. So that's what the meaning of only few outputs are measurable. Only x1 is measurable. Okay. So in that case, is it possible to estimate the states using the measured data? It means that can we find x2, okay, using this y? Okay, so that, in other words, in control words, we say that can we estimate? Can so x2 is the real value, whereas estimated value or observed value is x2 cap. Okay, so can we find x2 cap using the output? Okay, so basically these observers, okay, so they will reconstruct these missing state variables from the measured values like output here we have. Okay, so this is the basic idea. So the observers will give us a way to reconstruct so the missing or unmeasurable states. So that overall we'll be having in this case x1, x2 cap. Okay, so where x1 is comes directly from the measurements, x2 cap we are going to observing or estimating from the output. So hence we have this u. Once you have this u, x, you have this x, we can find your control input using this equation. So which is nothing but the pole placement. Once you know this x, you can apply the pole placement technique and place your closed loop poles at desired locations. Okay, so this is the idea of the observer. Is there any a doubt in this idea? Any query here in this? Okay, so that is first aspect. The second aspect is what if your measurements are noisy measurements? Okay, so noisy measurements. So then observers, what they do is they will help us to detect the sensor failures. by comparing the estimated states with the actual measurements. That kind of observer we call it is as a Kalman filtering. So we are going to see the normal observer and we are going to see the Kalman filtering. Okay. So the basic idea here is uh, pole placement technique assumes that all these states are available, but for practical cases, only we can only measure some states. We know other states we cannot measure. So the missing states can we estimate from the available states or available measurements. Okay, so that's this state observer is going to help us to do that task. Okay, so here, so for observability, basically handles these situations. Okay, so it will give us a way to check whether that estimation is possible or not. So as I said, so let's say in X, so x1, x2, x1 is available, x2 we wanted to estimate, okay, or we wanted to observe. So basically this notion of observability is, so whether the estimation is possible or not. So observability talks about possibility of estimating x2 or not. Okay, so where if you see this u is equal to minus kx, okay, so it basically requires this x. So x, we require that x continuously. Okay, so the state observer, okay, so estimates the state variables based upon the measurements of output and control variables. So, okay, so that's why what we do is we call this estimated one is x cap. Okay, so that is nothing but the observed state vector that directly we will use in the this equation. So this using this we can go for the pole placement. Okay, so instead of x we will be having x cap, which is nothing but the observed state. Okay, I hope it is clear. Okay, so let's see how exactly this state observer will do this task. Okay, so we have given system, we know these equations. Now let us consider the copy of the original system. Instead of x we have x cap. Okay, in place of x we have x cap. Okay, so that is the copy of the system. Okay, so something like we have one system here, we have another system here taking the copy. So this is x dot, this is x cap dot. Okay, now if you subtract these two equations, okay, so you get this error equation, error equal to x cap minus x. Okay, so if you subtract those equations, you get x dot e dot equal to ae. Okay, e dot equal to ae. So now this looks like a differential equation where x dot is equal to ax. Okay, if your a is negative, okay, if your a is negative, so you will get your x of t as something like e power minus at x of 0. Okay, so how does this looks like? It looks like this is t, this is x of t. Okay, so the variation of x of t looks like it starts at x of 0 and slowly reduces and go to 0. Similarly here, if A is a stability matrix, that means that eigenvalues of A are negatives. Okay, then your E goes to 0 ultimately. That we call it is as a exponentially convergence. Okay, so for every U, that is first case. Okay, so just by taking the copy of the original system and taking the error between the original system and the copy system, you can make the error goes to 0. It means that that gives an indication that x cap and x both are equivalent. Okay, so that means estimated state and the uh, current state, estimated state and the real state both are same. Now, what if A is not a stability matrix? It means that eigenvalues of A are not negative. All the eigenvalues may not be negative. Some may be positive. Okay, some may be positive. In that case, so this is our closed loop equation. Okay, simply what we are doing, so we are taking this the copy of the system and adding this constant, adding this ke. Okay, so where ke is the matrix, or we can call ke as the observer gain, observer gain matrix, and you are taking here actual output, that is nothing but the measured output, to the estimated output. Okay, so you have this simplified equations now. Okay, here in this x cap is the estimated state, c x cap. Okay, x cap is the estimated, c x cap is the estimated output. Okay, so the inputs to the, if you see this equation, the inputs to the observer are the u as well as the y. Okay, so where ke is called as the observer gain. Okay, so now observer again we have x dot minus x cap dot. Okay, so we have this equation now, like the previous one. Now this is our error equation when your a is the a is not a stability matrix. Previously when a is a stability matrix, this is our equation. Okay, here what we saw, if a is a stability matrix. Okay, so if all its eigenvalues are negative, so obviously the that leads error goes to zero, just like this. Now here this is our equation. Now our situation is like, so we have this A minus KEC, A minus KEC matrix. Okay, so what if again same thing, if the eigenvalues of this matrix, okay, if we get them as negative, ultimately that makes our error goes to zero exponentially, just like this case. Okay, just like this case. Okay, now our job is to make the eigenvalues of that matrix A minus KEC goes to 0. Okay, so eigenvalues of that matrix goes to negative values. Okay, so then we can say that, so the error vector asymptotically stable or convergence to 0. Okay, so then our design problem would be like this. Can we design, okay, can we design this K matrix, the observer gain matrix K? Okay, so in such a way that the desired matrix A minus KC, okay, so if and only if the plant is completely observable. Okay, so again, observer gain matrix Ke can be determined to yield the design matrix A minus Kc if and only if the plant is observable. It means that we wanted to choose our Ke, the observer gain matrix, in such a way that the matrix eigenvalues will goes to infinity. So the problem condition is, so the entire plant must be observable. Here our main job is to find, so the main job is to find this Ke. We wanted to design this Ke, that's all. Okay, so once we design this Ke in such a way that all these eigenvalues are negative, that makes this error goes to 0. Okay, asymptotically or exponentially. Okay, so now we can see this simple example. So we have this given system. Are there any queries as of now? Any
No,
queries?
sir.
Yeah. So if you're having any queries, please do ask me there itself. Okay, so that you will not to miss the link. Okay. So you see this example now we are given with A, B, and C. So the problem here is we wanted to design full state observer. Okay, for these desired poles. For these desired poles. So we will proceed in the same way. Like first what we do, just like the pole placement technique, where we first check the controllability check. Here we will check the observability check. Okay, here observability matrix is, so you know that is C, AC, A squared C, etc. A power n minus 1 C. Okay, here n is 2. Here n is the 2. So that's why we have up to CAC. So now the rank of 2 is, rank of O matrix is 2. Hence system is completely observable. Okay, so that means that hence determination of this observer gain KE, observer gain matrix KE is possible. First, that is the first check. Okay, we need to check the observability. So once the rank is 2, we can say that finding KE is possible. Okay, which can make finding KE is possible, which can make this the desired the eigenvalues should be at these locations. Okay, then what we can do is, this is our equation we have. Okay, so from this, what is the characteristic equation? Characteristic equation is, so for this matrix, okay, so that is Si minus that is Si minus of A minus KEC. This is the characteristic equation. Okay, so from this characteristic equation, you can substitute Ke as Ke1, Ke2, because we have n is equal to 2. Okay, then you are finding this is the with key. Okay, now compare with the desired. Desired means what? These are the desired eigenvalues we want. Okay, so minus 10 and plus 10. Okay, so desired characteristic equation is nothing but s plus 10 equal to 0, which leads to this equation, s square plus 20s plus 10. Now compare these two equations. Okay, so Ke2 is 20, Ke1 is minus 20 plus Ke1 is 100, you'll get is 120.6. Okay, so you got this Ke matrix. Okay, so this Ke matrix, if you substitute here, okay, so you will get, if you this Ke matrix, if you substitute here, so this you will have the eigenvalues, okay, minus A minus KEC as negative eigenvalues, which indicates that your error goes to 0 as time t is tending to infinity. That means error is getting 0 means what? So error is nothing but what? X dot minus X cap dot. Okay, where this is real and this is estimated. Okay, so it means that, so the real between the states between sorry, these are the states only. Okay, so the real between estimated is becoming 0. It means that the observer is can accurately predicting, okay, accurately observing the as state vector x cap. That's the indication. Okay, so now the question is, what are the different effects if you add the observer? Is there any doubt here till in this example? Any doubt here in this example?
Till now, no, sir.
Okay, okay, fine. So now we'll see once we add the observer, what are the effects we'll see. Now here you can see, so the first image where we have this system, okay, where we have this system. So what we are doing here is we are having the output here. We are having output here that we are taking at this point, multiplying with f and taking here. Okay, so ultimately the reference is r of t. Here you will get f of x. So this will be your u. U is equal to r minus f of x of t. Okay, that if you substitute here in place of u, okay, this system, this model, we call it is as method of state feedback. We are taking the states of the system as feedback and designing the controller. Okay, clear. Now the basic point here is this x. Okay, let's say our x is, the x vector is x1 x2. Okay, if this is only x1, okay, so it means that you can only take feedback of x1, so x2 is not available. In that case, we cannot apply this state feedback. We cannot take the entire feedback as entire states as feedback to here. Okay, in that case what we are doing is, so we have this output here, so output we are measuring and we are giving that output to the observer. We are giving that output to the Observer now is estimating the state, right? Observer now estimating or observing from the available output measurements or output values. Okay, so basically here what we are doing, we are taking the output as a feedback and developing the observer. Is this point clear? So here we directly give the state vector x, whereas here we get state vector estimated one, so which is given by the observer. Okay, so now just like this one, we have input here as this. The difference between above and below is the x. Here is the direct state, whereas here it is the estimated state. Okay, is this clear, this image? Any queries here?
No, sir.
Yeah, so this is the basic intention of doing adding the observer. Okay, so again same thing. So pole placement design assumes that the entire state is available for feedback, whereas in practical purposes, so we don't have the entire state. Instead what we do is we will estimate the state and then give that estimated state uh, as the state vector. So hence our design procedure will be having the two steps. Okay, so first step what we do is we'll find the gain matrix using the desired characteristic equation, just like the pole placement one. The second step what we do is we'll find the observer gain matrix, okay, ke, okay, to the desired observer characteristic equation. Is this point clear? So in the first step what we do is, okay, so we will find the gain matrix K, like pole placement.
Yes, sir.
Okay, okay, for the desired poles. Okay, so from the desired poles. Okay, so that is pole placement only. Then the second step, what we'll do is we'll find the observer gain Ke for the desired observer poles. Okay, so these are desired closed loop poles. These are desired observer poles. These are these two steps. Now we are going to see exactly these two steps with an example. Okay, so first let us see one by one. Okay, so we have this original system. Okay, and so now instead of x, we are giving this x cap estimated x tilde estimated state, right? Then our input becomes what, minus k x cap x tilde. Okay, so once you substitute that, so this is our observer system. Okay, this is the observer system. Then you have this error dynamics. So subtracting this from the observer system, this one. Okay, so combining both. Okay, so the first one, so this one, and the error dynamics, we have this equation. Okay, new system of equations. Okay, combining dynamics, we have x dot is equal to a bar x, where a bar is this matrix. A bar is this bigger matrix. Now again you see x dot is equal to a bar x. Okay, so that is the basic model we have with the combined dynamics. Okay, so now, so if you take the characteristic equation, because we are having the x dot is equal to a bar x. Okay, so to check the stability properties of this combined system, so you start with the a bar. Okay, so x dot is equal to a bar x. So you start with the characteristic equation. So Si minus a bar. Okay, what is a bar here? A bar is this entire matrix. Okay, so now take the individual terms. So then determinant is multiplication of these two minus multiplication of these two. So you have two terms. Okay, one is this term, the other is this term. Okay, so the product is equal to 0 means either first term goes to 0 or second term goes to 0. So what it says, first term goes to 0, it has only k. Second term goes to 0, it has only ke. Okay, it means that we are solving the above two equations separately. Okay, so that means we are designing k and ke separately. Designing k and ke separately. What is k basically? K we are defining by using the pole placement technique or state feedback. What is KE? KE is the observer gain, state observer gain. Okay, so we are designing them separately, even though we have added the both the dynamics here. Okay, both the original system or observer system dynamics and the error dynamics. We are solving them differently. Okay, so this is what the image looks like. So first, basically, forget about this down part. Okay, if you have only this part, if you have only this part, okay, so what do we do? That is basically original plant. How does it looks like? X dot is equal to ax plus du, y is equal to cx plus du. Okay, original plant which we wanted to control. Okay, so in case if your measurements will give you x, complete x, you can define this u, you can design this u as u is equal to minus kx, just simply by doing the pole placement technique. So you can go for the controller design, there is no issue, and place your poles wherever you are interested or desired locations. Okay, whereas once if you don't know this x, if x is partially available, only some states are equivalent to the output. Okay, so what you do, you design this observer. So you design this observer, this part. Okay, so you design this observer. Okay, so where the observer, what you are doing, so to the observer, okay, you will be having the two inputs. Okay, so you can see here this output is one input. Okay, so that you are taking, then so then the other input is from the u, also from this u, you can see this, the other input. Okay, so what you are doing, ultimately you are finding this x cap, you're finding this x cap by properly designing this ke. Okay, then after that this x cap you will be feeding back here minus k x cap. So this will be your state feedback controller. Okay, so then u becomes minus kx cap. Is this image clear? Any queries?
No, sir.
If you're having any queries, please you can ask me. Okay, so the top system is original plant. If your output is equivalent to the full state, directly you can control it using this equation, direct pole placement technique. If this y is not equivalent to full state, only it is equivalent to some of the states, there we are introducing the observer, where observer will take this output here. Okay, so by taking this output, it will generate x cap, which is the estimated state for all these states. Then that will be multiplied with minus k, then u will be equivalent to minus k x cap. That input we will give it to the direct original plant. Okay, so that's the whole idea. Okay, so here this system having two things. One is designing this k. Okay, another is designing this ke. Okay, so designing this k is the part of the state feedback design, state feedback control. Okay, and ke is you wanted to place your observer poles. Okay, so state observer gain. observer gain matrix. Okay, so you wanted to place them somewhere. Okay, and total you wanted to make the system stable. Okay, I hope this is clear. So we'll see in an example so that you'll understand much better. Okay, so you can see here. So assuming that you are using the observer state feedback control, it means that you are taking the x tilde as your state. Okay, x tilde is your state. Then we have this x tilde equation. Then after that, you are giving that x tilde to the control, feedback control. Okay, so this is observer equation, this is feedback control. Now using these two equations, okay, using these two equations, if you take the Laplace transform, if you take the Laplace transform, so I can easily find. Okay, so the input by output, not output by input. Okay, so you have this expression. You have this expression. Now these two equations we can show here for the given reference input 0. Okay, you have this plant. Okay, where this controller, okay, this controller is nothing but the final controller. Okay, where p is the plant. Okay, here I took u first and y next because u is the input here, y is, sorry, u is the output, y is the input. That's why we took input u by y instead of y by s. Okay, now this is your image. So it means that the final, this entire image, okay, so has been converted to this image. Okay, simply this is your controller, where this controller you are defining this K matrix and KE matrix. So we are designing the K and KE matrix. Okay, this is the plant. So using those K and KE, so this entire box, this controller, we are applying the input. Okay, so this we are calling it is as a observer based controller transfer function. Observer based controller transfer function. Okay, so let's start with the example, a comprehensive example. Okay, so the previous problem only, we have this system. Okay, we have this open loop system. Okay, now you are desired poles you wanted to place it, so these things. Okay, so minus 1.8 to j 2.4 minus j 2.4, so somewhere here. Okay, so I'll copy this one because we wanted to move the poles and see what is happening. Okay, so now, okay, suppose if you use the pole placement technique, what you do simply, so you take the u is equal to minus kx. Okay, then substitute in the basic equation, you will get x dot is equal to a minus bk x. Okay, so bk multiplied x. Okay, so what you do, so you take the characteristic equation a minus bk det, that is equivalent to s minus mu1 s minus mu2. Okay, so then you compare the coefficients. Okay, so find the K matrix. This is what we do in pole placement techniques. This is that K matrix, 29.6, 3.6. Okay, so it means that for this system, you wanted to place the closed loop poles at mu1 and mu2, you require this much gain. Is this clear? Any queries? You require this much gain. Okay, so assuming all these states are available. Okay, now, okay, so you're substituting here. Okay, so this is the input you wanted to apply after substituting that K. Okay, so now you can see here, the C matrix is 0 and 1. Okay, so that means it looks like this. C matrix is 0, 1, x1, x2. So what is that indicates? Y is becoming x2 only. It means that you know y means you will be knowing only x2. Okay, only x2 is available but not x1. Okay, it means that states are partially available. So the question is, how do we find the x1? Okay, so what do we do is we go for the observer design. We go for the observer design and find the estimated state as x tilde. Okay, x tilde. So then our input becomes like this. Our input becomes like this. So instead of actual state feedback control, we are taking the uh, estimated state feedback control. Okay, so here we wanted to place the observer at this location. We wanted to place the observer at this location, which are far from the desired pole location. What is our desired pole location? So our desired pole location is this one, minus 1.8. Okay, so we wanted to place very far. Okay, so desired pole location is yet to minus 1.8 here and here. So we wanted to place the desired observer pole location as somewhere here minus 8, very far. Okay, so that's the intention. Now let us find this KE matrix. Okay, so you remember this. Here the goal is to find KE such that the desired poles should be s is equal to minus 8 and minus 8. Okay, what we do? So we have these error dynamics with us. Okay, so you can find the characteristic equation. So equate that characteristic equation to s plus 8 and s plus 8. So this is the characteristic equation. Okay, s square plus, okay, so ke2s minus 20.6 plus ke1. Okay, equate that one to this. Compare the coefficients. You'll be getting ke as this 1684.6. That's it. Okay, so you already have the k matrix here. Okay, and this is the ke matrix. So design is completed. Now we'll see the response. Okay, so you can see this observer equation and input equation. So this is the observer equation which we know already. So substitute here. So these are the observer dynamics. X1 dot, X1 tilde dot, X2 tilde dot. Okay, so this is the transfer function. Okay, so now if you use the MATLAB, because you know the transfer function and plant dynamics. Okay, so you can use this MATLAB simple code and plot them. So you have this plant transfer function as given in the static of the problem. These are the for observer. Okay, so so combining both x dot and e. So with these initial conditions, x0 is this much, e0 is this much. Okay, so if you find the solutions for x of t and e of t using MATLAB and these initial conditions. Okay, so this is the plot. Okay, you can see for x1 and x2, x1 it is getting settled to 0, x2 also getting settled to 0. Okay, whereas error is stable getting 0 and here it is getting 0. This is the case when we choose, when we have chosen our observer poles are very far at minus 8. Okay, next. So try to move these observer poles very near to this minus 1.8 and beyond minus 1.8 also. Okay, so now you can see. So previously these are the things. Okay, so these are very left side very far. Okay, now these are the new locations. Okay, so they are very somewhat closer to the desired poles. Okay, so it means minus 1.8. Okay, so these are our desired poles. Okay, now you are choosing these as observer poles as minus 1.8, minus 2, very very close. closer to the desired poles. Okay, closer to the desired poles mu1. Again start with the same initial conditions. Okay, find the system response. Okay, so in this case, so now here you can see, so the error has not become zero. Okay, that is first point. Then settling time is increasing. Previously settling time has started from here. Now settling time is more than 4 seconds. That's the important point. Okay, this is one observation when we try to choose the poles closer to the desired poles. Okay, next, so try to choose the poles, third case, okay, very near to this omega 1. Okay, so it means that you are choosing poles, these are minus 1.8. Okay, so you are choosing the pole, one pole here at minus 1, another at minus 0.5. Okay, so right side of this desired poles, or we can say that they are close to the, so they are close to the z omega axis. Now you got your k matrix as this, ke as this. Okay, so it is observable poles. Now we have placed the right of the controller poles. Okay, so now again consider these three two initial conditions, same initial conditions. You can see here. So the error hasn't become zero. Okay, and the error is this much. Okay, so it kind of weird error. Okay, also the response is very slow. So it means that response is sluggish in nature. Okay, these are the three cases when where you have chosen three cases. So first one is very far from the left of the controller, where we have observed that the observer quickly corrects the estimation errors. Observer quickly corrects the estimation errors and decays much faster than the system response. Okay, first thing. Second thing is when you place them close to the desired poles. Okay, so the decay is not significantly faster. The third one is when you place them right side of the controller pole. Okay, so there is a estimation error. Okay, so the states are not decaying at all. Okay, so decay is very sluggish in nature. So this is the effect when you add the uh, state observer, when you design the state observer. Okay, so are there any queries in this? If you don't understand the basic idea,
No, sir. It's fine.
so the purpose of adding the state observer and designing KE and K and KE in all these three cases. Okay, so here basically what we are doing is we are keeping the pole placement as it is and adding the state observer. Okay, so that's the main intention.
Yes, sir.
Okay, yeah. Okay, next what we will do is uh, so we will see the quick review of the Kalman filter. Okay, as I said, so we are designing the basically we are going for designing the state observer. So the main intention is to estimate the states. Why do we want to estimate the states? So from the closed loop control system, so we are getting the outputs as measurements. These outputs as measurements, they are related to only some states, and other states we have to calculate by using these values. Okay, so it means that your state is not directly available. Okay, to estimate or observe the state, we are uh, using the state observer, or we are designing the state observer. So sometimes, what if, okay, what if your output measurements, so what if your output measurements are noisy in nature? Okay, so when they are in noisy, so the question is how to estimate, how to estimate the uh, true state, true state of the system. Okay, so in this case, whatever the observer, state observer, we design, so that is nothing but the Kalman filter. That is nothing but the Kalman filter. So basically, it's a kind of algorithm. Okay, so basically, Kalman filter is an algorithm. Okay, so what it does is, so the idea is, okay, so let's move to the next one. So basically what it does is it will this algorithm works by predicting the next state, okay, using the mathematical model, and try to correct it as and when the measurements are available. Okay, so let's discuss the idea here, the core idea. So the core idea of Kalman filter, so in short I am using as KF. Okay, so in every time step, at every time step, okay, so what Kalman filter does is, okay, so it estimate the state, it estimate state, okay, then, okay, so it actually estimate the state, then it will consider this uncertainty. Okay, so it is something like at every time step, so the KF maintains, KF maintains, it estimates the states, which is nothing but the best guess of the system. Okay, then it will also consider it will also maintain the uncertainty. So how confident the estimate is, how confident the estimate is. Basically what it does is it balances, okay, so model prediction, it balances the model prediction using the physics model, physics or dynamics. Okay, and then it also balances the measurement data. Okay, so that means the sensor readings. Okay, so basically this balance is controlled by what? This balance is controlled by something called as the Kalman gain. Balance is controlled by the Kalman gain. So you get the idea of Kalman filter. So basically Kalman filter, what it does is, so it has the dynamics. Okay, can you hear my voice?
Yes, sir.
Yeah, so it has the dynamics and it has sensor readings. Okay, so dynamics means the kinematics and the motion dynamics. So they will give us some value. Okay, okay, and in reality sensors will give us another value. Okay, so now the question is which one we need to believe. Okay, so let's say if there is a robot, for robot we have the motion equations which we are calling them as dynamics. Okay, So the motion equations, if we give the initial point, it will give us the next point. Okay, so that comes from the dynamics. Using the equations, we are getting the next point. Whereas if we use the sensors like GPS and all, they will give another set of points. Okay, so in practical, they may not match. Yes or no? They may not match. Okay, but dynamics we cannot avoid. At the same time, sensor readings also we cannot avoid because that is practical. Okay, so our the exact value, okay, the exact value somewhere in between these two. Okay, what this Kalman filter will do is it will try to maintain the balance between this model prediction and measurement. Okay, so that's how it will try to maintain the balance between these two, and it will give us the uh, state in between somewhere these two. Okay, so basically that balance is properly controlled by this Kalman gain. Is this clear? The idea clear?
These two things we have to do to get our K gain, Kalman gain.
No, not like that. So I'll tell you the idea. The idea is like we have a system. Okay, so
Okay.
let's say we have a car. Okay, so car having the dynamic equations. Okay, so let's say if we give the car an initial position. Okay, and if we say
Okay.
that the car is moving some 30 kilometers per hour. Okay, using those dynamic equations, after 1 second or after 1 minute, we can calculate where that would be. Correct? That using the dynamics. It means that using only equations. Is this clear?
Yes.
Suppose if you keep some GPS on the car and apply it practically, the
Okay.
GPS will give you another value of the position after 1 minute. Okay.
Yes.
Yes. So basically, the GPS is some kind of noisy. Okay. Suppose if the dynamics is giving 10 meters, okay, the GPS may give 11 meters. Clear?
It could be
Bec
different.
yeah, bit could be different because of noisy behavior of the sensors. Okay. Now the question is which one I should go for. Okay, so whether it is 10 meters or 11 meters. So basically this Kalman filter, what it does is it will try to balance these two things because they both are good, because sensors are purely practical, dynamics comes from the physics, we have to believe them. Okay, so but since these two are
Yes.
different, so what Kalman filter will do is it will try to do this iteration process and it will try to give you a value which is in between somewhere these two.
So
Okay,
one
so
is by calculating by physics,
yes,
like
yes,
dynamics,
yes,
what we are telling, and
yes,
sensor are
exactly.
the real-time practical values what we are getting it.
Yes, but
But
they are
we have to
sensor,
go
but
with
they are noise having noise.
so we
Okay.
have to go with both that will
No.
give
Kalman filter will use these both. Okay, and will give you a estimated state in between these two by balancing these two.
okay.
Okay, so if the sometimes if the dynamics will give you, let us say 50 meters. Okay, and sensor is 11 meters. Okay, it will not give much importance to the dynamics. It will believe in the sensors.
Sensors then.
Yes.
Okay.
Sometimes if sensor is giving 60 meters and dynamics are giving 10 meters, so it will give more
Then it will go
importance
with
to the
10.
dynamics. Okay. So that will be taken care by this Kalman gain K. Okay. So now we will see how this Kalman filter will do this uh, the balance. Okay. So there are two steps in this process in the Kalman filtering. Okay. So
So
first,
like the previous example, if the
yeah.
case was like 10 and 11, so
Yes.
what it will go with? Like if suppose we go with a 10 and 11, then what
Yes.
preference it will go?
10 and 11, and that we will
Like
see it will maintain the balance using this Kalman gain. Okay,
okay.
so it will give you in middle some value.
Means
Okay.
it could be like 10.2, it could be also 10.6,
Yes, yes,
something like
exactly,
that.
exactly, exactly. Yeah. So,
Okay.
but if you know actual value, let us say 10.5. If it is giving 60 means what? The noise is very
Then
high.
it means faulty, means
Yeah, yeah,
reading is
yeah.
faulty.
Yeah, yeah. So that we will see the simple example. So the
Okay.
Kalman filtering will be having two steps. One is prediction. Okay. Second one is update. Okay. So what it does is first using the model or dynamics. Okay. It will predict the state. Okay. Then using the measurements, it will update the state. Okay. So
Okay.
measurements and model. Okay, so in the prediction what it does is, okay, it will try to estimate the next state. It will estimate the next state. Okay, and it will also it will estimate the next state, sorry, by using the dynamics. Okay, dynamics as well as the uncertainty in the model. Okay,
Yes.
and here what it does is it will adjust. Okay, so it will use these measurements, okay, and adjust the predicted state. This is the predicted. Okay, so it will adjust the predicted state. Okay, and it will try to reduce the uncertainty. It will reduce the uncertainty. So we'll see exactly what these steps looks like. Okay, so now let us consider the mathematical model of the system. Okay, so it is our xk is equivalent to ax minus k plus wk, where wk is the noise, process noise. Okay, so that will
Okay.
be Gaussian noise. Okay, so where similarly, let's say zk output equation as hxk plus vk, where vk is nothing but the normal or Gaussian noise, something like this. Okay, it means that what? So from the existing system, we are adding two noise terms. Okay, so we already know that the xk is the state. Okay, this is what measurement. Okay, and A is the state transition matrix. So let's say state transition matrix. This is the output matrix which we know already. Okay, so this is the noise, Gaussian noise, wk and vk, where k is what? Q is the process noise covariance. It means that noise term in the dynamics. Okay, whereas R is nothing but the measurement noise covariance. Okay, so if we have this model, yeah,
So then the ZK is our measurement and R is our
yes, yes,
measurement noise.
yes. This is
And
just like our regular terms only. X dot is equal to ax
yes,
plus
yes, I am relating to that
bu,
only.
y is equal to cx plus du
Hmm.
only, where output y is nothing but zk here in the discrete terms.
And the
Okay.
above is our state. And what is
Yes,
our
yes.
Q is
Q is
state
the,
noise.
because this first equation represents the dynamics of the system. In that dynamics, how much noise we have.
So, like
Okay.
R is our measurement noise. So
Yes,
what
yes.
kind of Q? Q is what kind of noise?
Q is process noise, because this first
Okay.
equation will have the modal dynamics. In that modal dynamics, how much noise we have, that will be
Okay,
represented
we
with
got it.
WK.
Our above one is our dynamics, and the second
Yes.
equation is our measurement. Okay.
Yes, yes, exactly, exactly. So now our equations will be represented like this. So I'm not going to discuss how the equations came in. So first one is prediction step, second one is update step. Okay, so prediction step, what we do is we will estimate the next state. Okay, so given the fast state. Okay, so that is nothing but x cap k minus 1 k minus 1. So this is our first, this is the step. We estimate the next state. Okay, using the past state. Next, noise also we'll see, uncertainty estimation also we do using the past noise. P k minus 1 k minus 1 a transpose plus q. Okay, so that is for prediction state, prediction step. Next, in the updation step, what we do, first we find this Kalman gain, which is nothing but p k k minus 1 h transpose divided by h p k k minus 1 h transpose plus r. This is the Kalman gain. Next, what we do is we update the state. So whatever the state we have predicted, we update it. That means existing state, predicted state plus Kalman gain multiplied by the input to, the variation in the output. So h x k k minus 1. Okay. So similarly, we look for the noise term, uncertainty. So I minus k k h p k k minus 1. Okay, so I'm not going to discuss how these equations came, but just get the sense here. So what is that sense? So first step is we estimate the state. Okay, so this is what we are doing. Okay, so we estimate the state using the model. So using the model in the sense, using the first equation. Using the first equation, we are estimating the next state. Okay, then we update the process, we update the uncertainty. Then after that, we find the Kalman gain. We find the Kalman gain and we update the state. Update the state. Update the estimated state. This is what we estimated to this. So this is what we estimated. Okay, and we are updating here using this Kalman gain and deviation in the output. Okay, then we are updating the uncertainty also. Okay, so these are the steps every time we do. Is this clear?
But the notation what we are writing, that k with
Yes,
k k minus 1, that notation I'm not getting.
so k is a particular instant of discrete time. Okay,
Okay, at
here
k and like
k
at n
minus,
and n minus 1.
yeah,
Okay.
k is discrete time.
So
So
for
we are
both
starting
we are
at k minus
calculating,
1.
or
No,
okay.
no, we are starting at k minus 1. K minus 1 is already given to us. Using the dynamics, we are finding at k,
Hmm.
given
Okay.
k minus 1.
Hmm.
Okay. Then uncertainty also we are defining at that point of time. Then we are finding the Kalman gain. Then we are
Kalman gain
updating
is
the
the part
state.
of update. Okay.
Yes, we are updating the state. Okay. So from the,
Okay.
this is what
Hmm.
we predicted from the model.
Hmm.
Okay.
Yes.
These here measurements are available. First we predict it what model is saying. Okay, then as and when the measurements are available, measurements means what? H matrix only. Okay, so from here H matrix. Okay,
Measurement is
so
our H matrix.
yes, exactly, output matrix.
Okay.
Yes,
H is there.
so when they are available, we find the Kalman gain and we update our belief. This is what we believed, this is what we predicted.
Okay.
So from the
After
prediction,
every discrete time, this would our Kalman gain would get update, means
yes,
it.
yes.
Okay.
Okay, so then we update our state. Then again we update our uncertainty.
Okay, okay, okay.
Okay, now you'll see just calculations, then you will understand. Okay, so basically what this Kalman filter is doing is, I'll not simply blindly believe the
Believe.
measurements, okay,
Yes. Okay.
and I'll not simply blind the system model also. I will
Hmm.
combine them intelligently, okay,
Okay.
and try to give you the estimated state in between somewhere. Okay, how do I do that? I do that first by uh, predicting the state from the model. Okay, then as and
Hmm.
when the measurements are available, I update the state. Okay,
Hmm.
weighing by giving weightage to my confidence. This is the
Okay.
confidence. Okay, so
Huh.
what it does is,
So
if the sensor
credit
is
is our
very
model.
noisy, yes, if the sensor is very noisy, what it does, it will believe the model.
Hmm.
It to trust the model more. If the model is very uncertain, okay, what it does,
Then it will go with measurement.
yes, it trusts the measurements more. Okay, so that balance between these two will be done by this term, Kalman gain. Okay, so that's the confidence. Okay, so we'll see an example, you will understand in a better way. Let me write down the example. Okay, so let's say we have a simple robot tracking problem.
Okay.
Okay, so let us consider 1D case only. Okay, so 1D case means what? So a robot is moving on a straight line.
Okay. One dimension. Okay.
Okay, straight line.
Hmm.
Okay, so in this direction, let's say. Okay, so now we will do the calculations. Let's say here for the robot states are nothing but, okay, so xk is position and velocity. Position and velocity. These are the states. Okay, so let's say you have some sensors for both. Okay, so sensors are giving their values. So sensor is giving pk and vk. Okay, so assume that they are noisy. Whatever the values they are giving, they came up with high some kind of noise. Okay, so what you wanted to do is, so we want to estimate. So pk and vk. So that's why I'm saying them as pk cap, vk cap. Okay, so position is in meters, velocity is in meters per second. Is this clear? Problem setting. Okay, we have sensors for measuring position and velocity, but they are noisy.
Yes.
So still what we wanted to do is, we wanted to estimate both pk cap and vk cap. Okay, so let us say that we are moving with constant velocity. So constant velocity model, so that means delta t is 1 second. Okay, so every instant of time from here to here is 1 second moving. Okay, so now we can write, okay, motion as xk is equivalent to a xk minus 1 plus wk. Okay, so let us say how does this equation looks like? So it looks like this: pk is equivalent to pk minus 1 plus vk. Similarly, vk is equivalent to vk minus 1. This equation looks like this. So it means that this is what we wanted to proceed. These are the equations. So updated position is nothing but what? Previous position plus velocity multiplied by 1. Correct? So these are the dynamics. Okay, how do I write this? Pk Vk equivalent to 1101 Pk minus 1 Vk minus 1. Okay, plus we can that's it, correct? So this is nothing but what? Xk is equivalent to Axk minus 1. Am I correct? Okay, so these are the dynamics.
Yes, sir.
Okay, so simple constant model. Okay, so now let's add the noise. Okay, so if we add the noise, so yeah, these are the dynamics, and let us say we have Zk as Hxk. So where H is the, we can write this one as something like this. 10xk, that is nothing but pk. That means what? Zk is nothing but pk only. Okay, so basically 1 2, these represents our dynamics. Okay, is there any doubt here? Any doubt?
No, sir.
So this is Zk Hxk. Okay, so let's say this is 3, this is 4. Okay, now you look at the 3 and 4 equations. So what I do is I'll add the noise to this. Okay, so the process noise and the measurement noise. Okay, so that is xk equal to ax minus 1 plus omega k. Okay, so zk is equivalent to hxk plus vk. Now these are our equations. So where wk and vk are the noise, where we have a as 1101, h as 1 0. So wk as noise n0 comma q. So vk as noise 0 comma r. Okay, I hope this is clear. Okay, so let's choose the covariances are q as 0.25, 0.5, 0.51, let's say. Okay, similarly r as some 4. Okay, so this represents the covariances. That means that the uncertainty in the model and uncertainty in the measurement. Okay, so now we are starting it. Let's say our initial belief, the Kalman filter process we are starting. Okay, so our initial estimate, our initial belief only. Okay, so at time t is equal to 0. So we are expecting that. Okay, so x cap 0 comma 0 is equivalent to what? Let's say 0 1. So it means that a robot is at 0 meters and moving with 1 meters per second. So then you'll have the state as 0 and 1. Okay, similarly p 0 comma 0 is what? 10 0 0 1. Okay, so and let's say we got the measurements. We got the measurements are, let's say z1 as 2.0, z2 as 4.5 meters. Okay, so now the setting is ready. Is this clear? Any query as of now? Any query?
So the equation and the a value and h value would be given.
Yes, yes. H value
Okay.
from these equations we are from this equation we are finding a, from this equation we are finding h, from this equation
Huh.
we are writing like this. Okay, so now we are going to apply the Kalman filtering. okay, to estimate the
Yes.
states. Okay, so the first one is let's say for k is equal to 1, because at k is equal to 0, so this is our initial belief. That means k is equal to 0. Okay, so now we are starting at k is equal to 1. So we'll have two steps. So first one is prediction. Okay, so second one is the update step. Okay, so prediction is basically based upon the prediction is based upon the model. Okay, so update is based upon the measurements. Okay, so now prediction step, what we do, so we take the equations, these equations, these equations. Okay, you can see. So let me remove this. So we have to calculate these two things. Okay, so what we do, first one is x1 0. So ax 0 0. Okay, you already know the a, you already know the x. Okay, so that will be like 1 1 0 1 0 1, which will give you 1 1. Hope this is clear. Okay, next, so next one is p0, this one, sorry, p10, this one. Okay, so that is nothing but a is what, 1 1 0 1, and p is what, we already we have 10 0 0 1, 10 0 0 1, and a transpose is 1 0 1 1, plus q is what, q is 0.25 0.5 0.5 0.51. Okay, so this one, so what is that value we will be getting? So we are going to get the value as 11.25, 1.5, 1.52. Hope this is clear. Okay, so this is our first step. Okay, second step, so we have to take these points. So we take these, second step. Okay, reduce the size, we'll keep them here. Okay, so these are the second step. Okay, so what do we do? So we'll calculate one by one first. Okay, so first one is let's say measurement is already available. Okay, so for measurement for Z1 is 2.0 is available. Okay, so we can calculate this one first. Okay, so that is, so Z1, this part, Z1 minus H, sorry, Z1 minus Hx 0, sorry, cap 1 comma 0, that we can calculate. Okay, so 2.0 minus H matrix is 1 0, this one is 1 1, which you will get as 1.0. Okay, next we calculate this H P, let's call that is as this term as some S. Okay, S1. S1, how do you calculate? So first we'll calculate the H10, then you calculate the P value 11.225, we have calculated already, 1.5, 1.52. Next is H transpose 10 plus 4. Okay, you'll get what? 15.25. Okay, then you will get the Kalman gain, K1 as P 110 H transpose multiplied S1 inverse if this one goes down. Okay, so that will be like, so 1 by 15.25, so 11.25, 1.5, so you will get something, so 0.73, okay, 0.05. Okay, now this one, so x 1 cap. So the previous state x 10 plus, so k1 multiplied z1 multiplied minus x 10, 10, sorry. So 10 cap. If you calculate this, okay, so what we'll be getting, this one as 1 comma 1 plus, so Kalman gain is 1 and 0.73, 0.05. Okay, so you will get 1.73, 1.09, that is new state. Okay, similarly the last one, this one, so that will be like, so if you calculate it, you will be getting 2.95, 0.39, 0.39, 1.85. Is this clear? Any doubt? So what basically we are doing is, so this one is nothing but this part. Okay, next this one is nothing but this part. Next k1 we are calculating Kalman gain. Next we are calculating the new state, this one. Next we are calculating finally this. Is this clear? Okay, so finally after
Yes, sir.
step one, yeah, so finally after step one, so end of step one. Okay, so what do you have? You have P position as 1.73 and velocity as 1.09. This is in meters, this is meters per second. Okay, you can see this. Okay, these are the values. Okay, initially what are their values? Initially these are the values, 0 and 1. Now they were updated to new ones. Is this clear?
Yes, sir.
Yeah. So that is step one. Similarly, if you do for k is equal to 2, if you do for k is equal to 2, you will get p as position. Position as 3.824 meters, velocity as 1.563 meters per second. You'll get these values. So in this way, we will proceed. Okay, till you get the stabilizer values. Keep continuing these steps until you get the stabilizer values. They are your final estimates. Is this clear?
How we get to know that we reached to a stabilized value?
Oh, the values will not change.
Which value will not change?
These two values, they get be stabilized. I mean, if you go to K3, so K is equal to
Hmm.
3, if you get the same values, you can say that they are the estimated.
Oh, like three and four have a same value,
Yes, yes,
or
exactly.
two or three would be have a same value.
If K is equal to, for K is equal to 2, these are the values. If you do the calculations for K is equal to 3, if you get the same values, then you say that, okay, these are estimated values.
Like k equals to 1, I have a different value, and k equals to I have a different value. Then I will proceed to k3. Well, k
Yes, yes,
equals to
yes.
3.
Yes, till you get the constant values. The
Okay,
values will not
like
change much.
hmm.
Yeah,
Like
so those
n
are
with
the,
like k equals
uh,
to n value should be same with k equals to n minus 1, just a previous one.
yes, yes,
Till then I
exactly,
have to
exactly.
continue calculating.
Yeah, yeah, yeah. Okay, so
Okay.
that is how the algorithm works using prediction step as well as the update step. Okay, so it will try to see, it will try to adjust the values in between this model and measurements. It will not it will trust the model for some time, it will trust the measurement sometime. So
Depends on the values.
yes, exactly. It will try to put give the estimated value in between somewhere. Okay,
Okay.
I hope this is clear for Kalman filtering and state observer also. Okay, are there any queries in the Kalman filtering or state observer, controllability, observability?
So, do you have any more example? Means here at k
Yeah,
equals to 2, we get this. So at k equals to 3, we will get this also. That,
not sure. I have not done the calculations. So k is equal to
okay.
2. These are the values. If you are interested, you can continue the calculations. So check.
So, like if a
Okay.
question that at what value of k it's stable, so what should we write? 2 or 3? Means if 3 value is same with k equals to 2.
Yes, exactly. So k is equal to 2.
Okay, so 2 is we will take. Okay.
Yeah,
The
because
minimum,
k is equal to 3,
yeah.
k is equal to 4 also you'll get the same value. Hence, k is equal to 2 is the upper.
Okay, okay.
Okay. So my suggestion is in the 11th week, so Vasumati has explained her experiments with Kalman filtering. So collecting data and finding this gain. Okay. So I suggest you to strongly to
Ma'am
watch that
lectures are
video.
there.
Yes. So you watch it. She explicitly worked on the Kalman filtering for her robot experiments. So you will get more insight into that. Okay.
Okay.
Yeah. So if there are no more queries, we'll stop here. Thank you.
Okay.
So thanks a lot.
So till week 12 is coming, na? Where